Okay, looks like we lost a few people, but I think they will come in slowly. Welcome to this last class for today. So also the last of this numerics part. So as I mentioned today, I want to just cover kind of a big topic based on this idea of just finding effective state representations, making approximation on the state vector level. And this is a big complex topic with many different things, so I don't have time to do really on-hand things, but I will just want to give you a book to kind of have a path of where to look at if you want to do these things. Okay, but just before starting, I want to go back quickly to the third lecture because I didn't quite finish up. So let me just go back because we are still on this mean field level calculations. And I just wanted to quickly show also, because I did the mean field calculations all for these long-range interacting spin models. But it works equally well, for example, for the Gross-Petersky equation. So this here is my one-slide summary of the Gross-Petersky equation, so to just set the stage. So the way that I like to actually think about this is if you look at the full quantum equation for the field operator, right? So I can write down a Heisenberg equation of motion for the field operator, which I call psi x with a hat on top. Right? It's important to understand that this is really not a wave function. This is really instead an operator that destroys a particle at a certain position. So this is really in second quantization. And this is if I talk about the bosonic gas, just in free space with this contact interaction that was introduced. Then the evolution of that field, that quantum field, goes according to the Heisenberg equation of motion for psi of x, which looks a bit like a Schrödinger equation, but it's not. It's really a Heisenberg equation of motion. And then what one can do is this equation, it has sort of the free part. So this is just the single particle part, single particle kinetic energy and the potential energy. And then it has the interacting part, which in the classical limit gives rise to this nonlinearity. So fundamentally, I have, for example, some type of trap potential, and then I can compute the eigenstates of the single particle problem. Right? And then I can use those eigenstates of the single particle problem to expand my many-body system, which I do here. So I then say that my bosonic field operator is really expanded in these single particle eigenstates, because in second quantization, I can write my many-body operators in any orthogonal basis that I want. And then the Gross-Petersky equation simply comes out from making the following approximation, that I say that I have a gigantic occupation of the lowest energy mode in the oscillator. So I neglect all of the parts which go beyond that. And then I just, what I do is, because there are so many particles in this one mode, then I say, okay, I'll replace this operator here by just a classical complex number. And then you arrive again at this thing, psi of x, which is sort of a classical field, and then this gives you the Gross-Petersky equation. Right? So in a way, the way that I like to think about Gross-Petersky equation, it's kind of the opposite of what you do when you do field quantization. For example, if you start now, this was here neglected in this light atom interaction lecture, but usually what you have to do if you want to really look at spontaneous emission, you have to quantize your field. And the way that's the electromagnetic field. So then what you do is you start from a classical field theory, electrodynamics, the Maxwell equations, and at one point you write the solutions of this field theory as harmonic oscillators, and then one just makes these harmonic oscillators quantum harmonic oscillators. So then one really quantizes a classical field theory. Here I actually have a quantum field theory, and then I make it classical in a way. So, and then I get this nonlinear Gross-Petersky equation, which, as you have heard now by these beautiful lectures from Elin, gives rise to all of this beautiful physics. Especially two dimensions. Okay, all right, and again, equivalently, one can also derive the equation as Helene has done when one does this kind of product state ansatz. So exactly the same as for the spin models. If I say that all the atoms are in the same state, in this phi-0 state, and I say the state of this condensate is a product state of this, then I arrive at this Gross-Petersky equation. Okay, but back to the numerical point is, so now I can use this integration of this Runge-Kutta method, for example, in order to evolve this equation. The way I have to do it now, of course, because this is now an equation which is defined on a continuous space. Right? So fundamentally, the first step what I have to do is I don't only have to discretize time, as I did, but I also have to discretize space. So fundamentally, I have to introduce a grid. So here I just do exclusively simulations in one dimension, just for simplicity. But in 2D, it works exactly the same. And then simply I have to define my wave function only on certain points on a space grid, and the spacing has some distance a. So I have a certain length of this box, and so on. I don't want to go too much into the details here because I really today want to just get concepts across, so don't get hung up on any details too much, please. And then the important, maybe conceptually most difficult part here to write this kinetic energy operator on this grid. But for that, one can just simply use sort of the discrete form of the second derivative, right? So the kinetic energy is just in continuous space, second derivative of the wave function. And the second derivative I can just write as psi x plus a minus psi 2 psi of x plus psi x minus a divided by a squared. Right, and my a is now finite. My alpha is not infinitesimal. And then if I write this thing in a matrix form, so if I define my state to just be defined at these certain points here, so I call it psi 1, psi 2, and so on up to psi m, then I find that this kinetic energy operator is this tridiagonal matrix. And that's kind of funny, really, conceptually even, because what this means is that really kinetic energy in continuous space, if I put it on a grid, it's really just the hopping of an excitation from one side to the next. Right, so here, if I write this in this discrete form, I can really say that this is identical to some lattice physics, where my particle here, this nearest neighbor off diagonals, just give rise to a particle hopping from one little side to the next one. And this is what the second derivative does if I discretize this. Right, so it's actually quite fundamental. And this is also quite funny because then really conceptually, this is again models that you will hear about next week, these optical lattice models. So if I take, for example, this Bose-Hubbard model I also briefly talked about in the first lecture, there you have bosonic particles sitting on individual sides. They can hop between sides, and then they interact when they're on the same side. So this model is really completely equivalent to the continuous space quantum model, only just really defined on a real grid, which is your optical lattice. So there one really imposes this grid, but conceptually it's exactly the same as taking a free space problem on an infinitesimal small grid. Okay, and then again, one can make some estimations here for the Bose-Hubbard model. If I think about how big my state vector can be when I really have a finite grid, then again I get these gigantic Hilbert space sizes that I cannot really deal with. But if I make this mean field approximation, so if I make this field classical, again, I just really dramatically simplify this only to state vectors which are linear in my grid size. Okay, the same as really for the spin model. Okay, and then I just can do my Runge-Kutta method. I will not, as I said, I will not go hands-on through this, but I do the same thing as I always did before. I define kind of the function that does the right-hand side of this equation. Right, so here this is now nonlinear in the sense, the nonlinearity enters here, that the function here just has sort of the single particle part applied to my state. And then I have to add this nonlinear part, which just depends on the state at this time. So it's quite simple. And then with this function, I can again write my Runge-Kutta fourth order time step and do some time evolution with this. So I want to just show some example of time evolution in this setup because it connects to something that I want to talk at the very end of today. Okay, so what I do here in this kind of fun simulation is first I start with like the ground state of the system if I just add an harmonic trap to the system. So I add an harmonic trap here in this V of x. I sketch it here as this gray line. And then I compute the ground state of this problem, which in this case I just can do by the evolving in imaginary time, which is a method I don't really have time to introduce, but it's kind of funny if you have a time evolution method available. You can also just switch the time to negative imaginary, and then the evolution in imaginary time will lead you to the ground state if you keep your state normalized. Right? So this is really, you cool the system. It's like e to the minus beta h. So you start to cool the system into the ground state. And that's what I do here. So I start with the ground state of the system. And initially, I just set the nonlinearity to 0, which in that case, I just really get single free particle quantum mechanics as you learned it in your first quantum mechanics lecture. So here, nothing. Here, the interaction doesn't play any role. Okay, and then I take this system, and then I just want to kick this system a bit. And the way that I do this, I just apply a phase gradient to this wave function. Right? So this gives this whole system a kick in momentum space. the best way to see is to look at the Fourier transform of the wave function, because then this transformation here just sort of translates the momentum distribution to a finite momentum. And then I can kick the wave function and look at the evolution, and then something like this happens. So this is really quantum mechanics, as you know it from the textbook. I can show it again. So it's just the wave function goes in one direction, at the same time it diffuses, so the wave packet becomes broader, and one can compute this, of course, analytically. This is really quantum mechanics in 1D of a particle. Okay, and the same I can do, I can kick it a little bit faster. So here I apply a bigger phase gradient to the system. Right before I had Ka 0.2, now I have 0.4, and now I kick it like this, and it moves just faster. Okay, of course, what we are interested in is sort of the interacting part, the Gross-Petersky part. So now if I turn on this G, if I turn on the interaction between the particles, the first thing you see is in the ground state calculation, you see exactly what you learned in the BC lecture. You get this Thomas Fermi profile, right? Compared to before, where there was this Gaussian ground state wave function. Now it just looks like the inverted potential that you have here, except for these little edges here, where then it flats off. And this is now the ground state of this BC in this harmonic trap. I shouldn't call it BC. This is 1D, but I will come to this later. Okay, and now I do the same. I give it a little small kick, and the whole thing starts to evolve again. And now it actually becomes broader much more quickly. Here you see some funny effects, some funny wiggles coming in. Any idea why this is the case? Sorry? No, it's not at the minus 15. That's usually always the answer. No, but here's just because I decided to define my system on a certain box. And you see now my classical field, it becomes too large, so I start to see finite size effects. Because I use periodic boundary conditions, as you have seen, so it keeps going around, but now it just gets too big. So this is non-physical. I would have to make my box larger, of course, in order to simulate this. And now finally, if I do something that I did before, I kick it a bit stronger, and then something funny starts to happen, as you will see. So this thing starts to kick over, and catastrophe happens, and everything goes to hell, essentially. Okay, and this is something that is quite known in the BC. It's known as the dynamical instability of the BC. And it is all quite beautiful to see this effect here. The problem is it's really wrong, because what I show you here is 1D simulations, and as you already should have heard as a warning, in 1D, this Gross-Petersky equation is not necessarily a good approximation. Right here you have a very low connectivity, and this mean field is actually not working, just in the same way that mean field was not working for the spin model when we were going to the high excitation case. So we have to do a bit better than this, and I will show you something at the very end. I will show you the exact calculation of this, not for the free space model, but for the Bose-Hubbard model, which is equivalently really the same thing here. Okay, so this is I wanted just to get out of the way. Good, but now I come to the actual fourth part of the lecture. So this is, again, the full summary of what we did now so far. So really the idea was to go away from this full Hilbert space description of the wave function and just go to a corner of the Hilbert space. So far we did it only with the product state assumption, making the problem mean field. And then we had the nonlinear equations, which we solved for this Runge-Kutta method, and now we analyzed where this is valid. And this 1D GP equation was one case where it's actually not valid. Okay, and now this time, what I want to do is I want to have kind of 4 parts. So first, I really want to introduce, because I talk about matrix product states, or what people call so-called tensor networks nowadays, I will just introduce what is meant by that, and also just say quickly how to code this type of tensor network things. It's really not difficult. It's just the codes become kind of long now already. Then probably the important part, I want to introduce, or I want to talk a little bit about what is bipartite entanglement, and how entanglement conceptually is actually an interesting quantity, because it tells you how much you can compress information in a quantum state, and this is the connection I want to really make. And this is really the key idea behind these so-called matrix product states that I then want to introduce in this third part here. And I want to just very briefly mention one algorithm to update to time evolution with matrix product states, And this algorithm is called time-evolving block decimation algorithm, or TEBD. As a warning, they have horrible acronyms in this field. I mean, this is historically, they have names that nowadays you have no idea anymore why are called that way, these algorithms. But this is conceptually the easiest algorithm to work with matrix product states, and this is the one I want to introduce. And then finally, I want to show some examples where this MPS thing can be really helpful and really useful. All right, but step by step. So I want to start with this idea of tensors. Okay, so I want to go back to a very fundamental thing again. And here, for now, I use sort of a bit of a quantum computing language. So I want to, let's imagine we have, again, a state that's just given of 4 qubits. And here I use this kind of quantum circuit notation, saying where each of these lines means just the state of a qubit, so, or a spin, again, if you like. So I have the basis states for each of them, which can be 0 and 1. So I have 4 qubits. I have a total of 16 different basis states of my state vector. Right, and then if you open a book like Nielsen Zhuang on quantum computing, then you see quantum gates. Right, and then quantum gates are usually something, they're written as this 4x4 matrix. This is sort of an entangling gate, that's controlled NOT gate. And it's a 4x4 matrix because it acts on 2 qubits out of these 4 qubits. So for example, a controlled operation on the second qubit, and then conditionally on what you measure here, you do a flip of this 4th qubit. Okay, good. So as I wanted to already, well, as I mentioned last time already, I want to rethink a bit the concept of state vector and gates, and instead of writing them as vectors and matrices, I want to write them as high-dimensional tensors. So conceptually, just let's start with the state. Right? Usually, before I wrote my state vector as this d times 1 vector, where I have all these 2 to the n elements in this vector, complex numbers. But then I know if I go especially to these quantum computing pictures, I have the basis states, which are defined as all of the combinations of the bits here. So I have the 0, 0, the 0, 0, 1, the 1, 0, and all the 16 different states. And what I call here the index I, that runs from 0 to 15. Sorry, if I started 0, I should go to 15, not to 16. Always confusion between 0 and 1. So I can write it like this. This index here runs from 1 to 16 or 0 to 15. Or I can write it just like in this way here, where I just sum over many, many small indices, which are all just 0 and 1. And then these indices, they sum over the state of these individual qubits, which can just be 0 and 1. Right? So what I then conceptually do is that I conceptually transform this vector to a high-dimensional tensor. So this is a thing that has many different indices coming out. And I can do precisely the same also for this gate, so for this C0 unitary operation. Right? So my C0 is also something that just acts on 2 qubits, and it's defined here on a basis which is 4-dimensional. So I have indices running from 0 to 3 in this notation here. But then I can also rewrite this as a tensor which has 4 indices, sort of, if you like, 2 input indices and 2 output indices. So please don't look at all of the details of this equation. They are super ugly. And I just put a few here just to show that they are ugly, because I will on the next slide introduce just a way to make things look much, 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 much nicer. Okay, so the bottom line is here I can write this 4x4 matrix here also as actually a 4-dimensional tensor which has 4 indices. That's what I call a tensor here. And then if I want to apply this C0 unitary to my state, right, then I have to do something like this. I have to sum over all of the indices that are in my Hilbert space, and then here I have to do this actual summation of this gate applied to my state. So the prescription for updating a certain amplitude of my state in the tensor would be given by this. Right? So this is actually a quite simple step here. So this is just really do the summation over the index of the second qubit and of the 4th qubit, which is the 2 indices here in this tensor M. And then I get new qubits out, which are A2 and A4. And I have to perform now the summation over these indices, which is the same in this tensor here and in this tensor. Okay, so of course, I do not want to work with the sums of like many qubits. So therefore, what people do in this community, one introduces actually a relatively nice diagrammatic notation of all of these tensor operations, and this is what I want to do next. Okay, so also one could simplify it, for example, using the well-known Einstein notation. Right? You could also just say, if I have joint indices here, I just sum over them automatically. But what's maybe even nicer is to introduce kind of this thing, what I do here. So imagine that you have a diagrammatic notation when you just draw a kind of box here. Then what I mean by this box is just a number. Right? So this is a complex number, which I call Z, and it has no index to it. It's just really one single number. And then if I have this box, but I draw one line to it and say, I'll say a little d1 here, d1 should be the dimension of this line. Then what I mean by this, I mean just a vector with one index. So one index is one line, and this index runs from 1 to d1 over this. Right, and so on and so on. I want to find like a matrix, then I have two indices, one with in dimension d1, the other one d2, and so on, and I can make it 3-dimensional, 4-dimensional, and higher dimensional. It is just like a diagrammatic representation of these high-dimensional arrays. And then what's important, what's quite nice, is then that I see I can just do this kind of what's called contraction of the tensors, just summing over indices. Now, what I do is, if I write down something like this, if I draw here this thing here, which has one index coming out, so this is a vector, then I have this thing with the two indices coming out, which is a matrix. Then let's imagine I let this line go away, disappear, which I call a contraction. I end up with a new thing coming out, which is again has one index, which is a vector. Right? So this is really a vector matrix multiplication. This vector V here has one index. This matrix has two indices. One index is the joint index of those two. And here I just sum over all of this dimension, which gives me a new vector element. And so on and so on. And now I can really, instead of writing these complicated sums, I can just easily also understand what it means to, for example, contract a matrix to a 3-dimensional tensor over one index. So that's one nice diagrammatic way of thinking about matrix multiplications in higher dimensions, if you like. What's computationally very nice about this thing is that I also see immediately sort of how much does this operation cost if I do it on a computer. Right? Because all I have to do is I have to really count the amount of indices that are involved here. So if I want to, for example, here compute this new vector v tilde that's coming out here, right? I know that for each of these values j, I have to kind of do d1 multiplications, right? Which is the elementary operation I do. I just multiply complex numbers. And now here I know that here I have d multiplications. I have to do it for each of these j elements. So the complexity, the computational cost that this one takes is something of the order d1 times d2. This is what the matrix vector multiplication is going to cost you. Okay, and the nice thing is if I have more complicated things, I can immediately say how much it's going to cost me, because now I just have to count the indices which are involved here. In this case, I have one d involved. I have a chi here, and a d here. So this is d squared, chi squared multiplications in order to calculate this new object here. Right, so this is really kind of diagrammatic thing, helps you to think about how to do contractions sort of in the best possible way, because you can kind of think about which do I contract first, and so on, and then you can say, okay, if I do it like this, then I can get contractor tensor networks in the cheapest possible way. So that's why this diagrammatic notation is quite useful. Okay, and just to familiarize with this notation, it's just, right, so what I was calling a state vector before with this single index, which was really just this one index of this one vector. Now I just write a state vector, something like this object here, where I have a total of n lines coming out. Each only have a dimension of 2. Right, and the connection between this and this is just by combining these indices into one index. Right, that's how I can go from this state tensor picture again to the state vector picture. But what I want to convince you here is that keeping things in this kind of tensor language can actually be quite helpful. Right? Even if you don't use any matrix product states, as I will introduce them, But even now say that I want to really do this application of this gate to my state tensor. Right, so before, maybe look down here first. So before I had just written everything as a state vector and a matrix, even if it's a sparse matrix, I had a sparse matrix applied to the vector. And my full C0 matrix in the full Hilbert space would not be a 4x4 matrix, but it would be a 16x16 matrix. So here, if I would really contract this gate, which is this matrix, to a state vector, I had a 2 to the 4 dimension here, 2 to the 4 dimension here, and I have to contract this. So this is going to cost me 2 to the 8 multiplications if I do it that way. Of course, I use sparse matrices, and they are smart enough to save some time, but still fundamentally, this is the number of operations that I need technically. But now if I write everything in this tensor language, I see I can actually do it smarter, right? Because I don't need to contract over this index I1 and I3. The only thing I need to contract over is the index B2 and the B3. This is my gate now for the C0 operation, and it only acts on the two indices, so I just really contract it only in such a way that I keep these indices open and I make those indices disappear. Right, and now if I start counting the indices, I have 4 two-dimensional indices here and two two-dimensional indices there. So that actually I can do the whole thing just in 2 to the 6 multiplications. Right, so this just helps me to avoid doing some unnecessary multiplications that I don't even know need to do, because I know that my operation only acts on a subpart of my system. Right, and that's already why sort of thinking about this not in terms of matrices and vectors, but instead of tensors contracted with other tensors, can help you to actually optimize any type of operations. Right, so everything what we did before, we could also just do with these tensors, for example. And it would give us actually a little speed up. Okay, so far so clear. So it's just really just a different way of thinking about these things. Okay, I want to spend just a few slides to just show you like how one would write a code to do this type of tensor contraction ideas. So I want to stay with this example of this simple 2-qubit gate applied to my state. Right, so now if I define my state tensor, which I call C here, right, I now define this really as not a state vector, but as a multidimensional array. Right, so I define some dimensions. So for example, 2, 2, 2, 2. So this means these are all the dimensions of the index that I have. And then I just create here like this vector which is filled with always zeros in the beginning. And the nice thing about this is also now if I want to, for example, take a state like 0, 1, 0, 0, right, I can just write, set the elements 1, 2, 1, 1. Again, counting. In Julia, they start counting at 1, which is actually not quite my favorite, but okay. Nobody's perfect. But so the 0, 1, 0, 0 translate to 1, 2, 1, 1. And you have to only set this one amplitude in this tensor to 1, and then this is this state. Okay, and the same for this now 4-dimensional tensor that gives the C0 gate. I can just create it in a relatively intuitive way. I would have something like, I know for my C0 here that the 0 state maps to the 0 state. This is the first line, so the 0 state here I have to think from the back to the front, because this is how I want to order my qubits. It's just a choice. I mean, you can order these dimensions as you want, but then once you order them, you have to stick with it. Here, I just ordered them that the two indices I want to contract over are in the end. So then I say, okay, this is mapping 1, 1 to 1, 1. This is mapping 0, 1 to 0, 1. This is mapping 1, 0 to 1, 1, because this is when you flip the second bit. And then the last one is mapping 1, 1 to 1, 0. Again, flipping the second bit, qubit, sorry. Okay, and this is just how you define these state tensors, just high-dimensional arrays in the memory. Now, the question is, how do I do these contractions over these state tensors? And I will show you two ways of doing it. So the first one would be, of course, I can go crazy and write loops, right? So now I can really literally do again what's written here. This is a sum over two indices. And I have to do the sum over these two indices, but I have to do it for all over the 4 indices here. right? So I can really translate a sum into for loops, which is quite easy to do. Translating a sum into for loops, it's just I sum over all of the indices of this tensor here, because each of these elements I have to get. So this is for I1, for I2, for I3, for I4. These are all just sums that run only over 2 elements. And then here in this inner loop, I said this is now the element I1, I2, I3, I4. This I start setting it to 0. And then I loop over this here and do the multiplication, adding each term of this sum of B2 and B4. Right? So this is some way that I could write this contraction. It's, as you see, probably not the most ideal way because it's really cumbersome to write it that way. But maybe one nice thing is you can again immediately see why this costs you 2 to the power 6 elementary operations, because I have these 6 for loops that are showing up here. And here in this loop, this is the one that this operation I will do 2 to the 6 times. So 2 to the 6 multiplications of numbers show up here. Okay, but I don't recommend using this. What I would recommend is actually doing something like I've written it here. And this is just because fundamentally this type of, okay, so this is a bit advanced technical stuff, so you can also fall asleep if this doesn't interest you. But fundamentally, any type of tensor contraction is still a matrix multiplication. Right, so if I have something like this, let's say I have a tensor A and a tensor B, right? If I just by chance have my indices arranged in such a way that this index C1 and C2 is at the end of this tensor A, and at the same time the index C1 and C2 is at the beginning of the second tensor B, right? Then again, I can just combine these 2 indices into 1, and I can combine all the other indices also into 1. And then this is just a matrix multiplication. So one can reduce all of these contractions of tensors really to multiplications of 2 matrices. And this is quite recommendable because computers are really good at matrix multiplications, mostly thanks to computer games. You have to do a lot of those because you have to rotate in space going around. Especially graphics cards are extremely good at this. So now there are really advanced libraries to do these very efficient matrix multiplications, not only on the CPU, but you can also go on the GPU. But of course, one needs a bit of work to do that. The explicit way of doing it is that one just has to permute these indices. Right? So in the example that I have here, I defined my matrix M already in such a way that, where was it? The indices that I want to contract over are already at the end. So I don't have to do anything to my matrix M. All I have to do is I have to reshape it again in a 4x4 matrix. So there are 2 keywords that are very important. The one is permute dimensions, and the other one is reshape. Right, so this already has the right order, so I just have to kind of tell Julia to think about this as a 4x4 matrix instead of a 4-dimensional tensor combining the indices together. For this C vector, on the other hand, I have to just change the dimensions. I have to do some permutations, right? Because now I have to bring, here the indices are at the end. So now for the C, I have to bring the indices to the front. So I have to put them into this order, which I can have to do with this permute dimension command. And this adds, of course, some overhead. Overall, it's also a bit annoying because it has to allocate some extra memory. But this matrix multiplication, then it happens here. It's so fast that this really typically definitely pays off. But of course, it's kind of annoying to write code like this. It's not very intuitive. It's not very nice. But then to make this better, there are a lot of packages out there which help you a lot. Here I just show one, which is called tensor operations, which is quite beautiful because you just have to say you have your tensor M, your tensor C, and you just really write it like this with the indices. And here it recognizes that these indexes are exactly the same. And then it does all of these permutations in the background for you and does then the matrix multiplications. And then you can write these tensor contractions in a much, much more efficient way. And there's tons of packages out there. This is one I like in particular. But of course, it still adds some overhead to your calculation. So if one does it manually, one can usually squeeze out a little bit. But then it's a lot of work because then you have to write a lot of these permutations in the best possible way. Right? Because sometimes you have to contract it in an optimal way. And then if you think about this, then you can save some time, which otherwise this routine has to think about it first. So again, swapping brain time for CPU time or GPU time. Okay, and that's all I wanted to say about this idea of tensors in quantum physics. So if you ever have a many-body system, which is a composite system of several subsections, it makes sense to write things as not vectors and matrices, but instead as tensors, which you contract to each other. Okay, and this tensor notation is really key for what I'm going to talk about next, and this is really this idea of these matrix product states. So as the name suggests already, it's kind of a generalization of a product state. So far we did mean field, which was only product state, and matrix product state helps to go beyond this. So with so far we did simulations on this mean field corner, and now we'll make this corner bigger with this new class of states. But in order to understand why this works, I have to take a little step back, and I have to say a few words about bipartite entanglement entropies. So really some main concept of quantum information. So entanglement, just as it's defined for a bipartite system, what do I mean by that? So imagine you have some type of many-body system. It can be spins, it can be bosons, or it can be whatever. And let's say you have a pure many-body quantum state of that. Right? So then you can split this state into two subparts. Let's call it block A and block B. And then just by definitions, you call these two blocks entangled with each other if it's not a product state. Right? That's the definition of entanglement. It's just something that you cannot write as a product state. Okay, and the question is like, how do you quantify this amount of entanglement? And the core idea here is to look at the state in a subsystem. Right, so I want to look at the state in my subsystem of the block A. And how do I get it? I get it by just tracing over the part B. The same I can do for the subsystem B by tracing over the part A. Right, and now you see very easily if you take a state which is not entangled, which is a product state, right? If you build here this pure state density matrix, psi, ket psi, bra psi, and if you trace over the subsystem B, you will just get the pure state in the system A or the pure state in the system B. Right, so now again, as you have also learned in the first lecture where there was some talking about the idea of pure states and mixed states, so here the state doesn't have any entropy because in principle you know exactly what the quantum state is. There's only one of them and it's not an ensemble of different states. Which means that this state doesn't have any entropy. Right, so this is quite different for when I take an entangled state. Let's take an example, which is the easiest one. Let's just take 2 qubits, and let's take one of these maximally entangled Bell states. Right, if you do the same calculation now with this Bell state, so I built the full pure state density matrix of the composite system, but now I trace over B. Trace over B is summing over the 0 in B and the 1 in B. But this one gives me here all the 4 different combinations of these products. But now I see this partial trace that I do in my subsystem B. It's going to kill this term. It's going to kill that term. Because here this is for B state 0, B state 1, and here this is B state 1 and B state 0. Right? So these terms, this partial trace is going to cancel these terms. So I end up in the density matrix which is just 1/2 the state 0 and 1/2 the state 1. Right? So here I go to this maximally mixed states, which is nothing but the classical ensemble of the state 0 and the state 1. Right? So I prepare these states many times, 50% the 1, 50% the 0. I give you this classical ensemble, and this is going to be that state. So this is a state which has the maximum entropy. So the idea of entanglement entropies is just I compute the entropy of this state, and then this gives me a number. And this number will just tell me how much entanglement there is between these 2 blocks. And there are several types of entropies that one can use. The most common one is the von Neumann entanglement entropy, which is the Shannon entropy in classical information. But there are other entropies. One can use Rényi entropies and so on. Okay, so the idea is one defines the von Neumann entanglement entropy like this, like minus trace A rho A log 2 rho A. And this is always, I find a bit confusing because here this is a logarithm of a matrix. And then you may ask, what does this mean? So what it really means is that I take the eigenvalues of this matrix. So I compute the eigenvalues of this rho A. And the eigenvalues of a density matrix are always a probability distribution. And from this probability distribution, you compute the entropy with the usual Shannon entropy. And one can show, I'm not going to do it, but it's quite simple, to see that the entropy of the subsystem A is the same as the subsystem B if the state of the total system is a pure state. All right, so far so good. So one can now ask, so what are the limitations of this entanglement entropies? So let's define now this entanglement entropy, not just for 2 qubits, but for a big system. So really, A is my reduced density matrix of a big block of the system. So I get a lot of potential eigenvalues of this reduced density matrix here. And now I can ask, okay, what is the distribution of eigenvalues which has the lowest entanglement? Well, it's the one where I only have one eigenvalue, being 1, and all the other ones being 0. Right? Just like in the example of the pure state, when I say I have something like 0, 1, a product state, then my reduced state is just 1, 0. It just only has one eigenvalue. It's fully defined. It has no entropy at all because I know exactly what my state is. So one eigenvalue and all the other ones are 0. And then you see easily if you have one eigenvalue, this entropy is -1 times the logarithm of 1. This is going to be 0 because the logarithm of 1 is 0. On the other hand, if I go to the other extreme and ask what's the maximally entangled state that I get, well, for 2 qubits, it was when I wrote my reduced density matrix with these 2 eigenvalues here, 1/2 and 1/2. And this is generally true, right? If I have a probability distribution and all the probabilities are just 1 over the number of probabilities that I have, then I have maximum entropy. I have no knowledge at all. So clearly, the maximally entangled state is where all of these eigenvalues of the reduced density matrix are the same, and they are 1 over the dimension of your sub-Hilbert space. Right, so the largest entropy you can get is the logarithm now of the dimension of your Hilbert space. And if your subsystem has 10 qubits, the dimension is 2 to the power 10. So then the logarithm of this is 10, so the maximum entropy that you could potentially make is 10. So I think a better way to think about it is that you have your 2 blocks, and if I give you only one block, then you have that state and there's some entropy in this, which means you're lacking information of the total state. And the same is if you get the block B. So it means there's some information in the correlations between the block, and that's what you call entanglement. Yes, I give you the quantum mechanics description of what it means if you have access to one subspace. Then the state is effectively just given by a partial trace over the rest of the state. Well, if it's entangled, you need to have the whole state in order to have all the information. Then the whole state is pure, but your subsystem state is mixed. If A is pure, then B must be pure, yeah. I agree. Sorry, I didn't catch this in the beginning. Okay, like for example, for 2 qubits here, then I get, for the maximal entangled state, 2 eigenvalues, both are 1/2, so I get -2 times 1/2 logarithm of 1/2, right? So this is going to give you logarithm of 2, right? This I turn into a minus sign because this is minus logarithm of 2, minus sign goes away. This goes away, 2 times 1/2 gives you 1. Because my sub-Hilbert space has dimension 2, and the maximum is the logarithm of this, which is 1. I always think logarithm space of 2 because I think it's the most logical for this information field. Okay, so great. So the question is, how do I compute this in practice? Because I know now that entanglement entropy is a kind of useful quantity to tell me how entangled my state is. Right here I have a product state, and I know it's a product state if the entanglement entropy is 0. So how do I compute this for a large system? And here the trick is what's called the Schmidt decomposition, which maybe some of you may already have heard, which is this conceptually exactly the same as a singular value decomposition of this coefficient matrix here. So this is basic linear algebra textbook stuff. A singular value decomposition says if you have some matrix, let's call it C, then I can, and this works really for any matrix, doesn't have to be a square matrix, it can be any matrix. I can always decompose it in such a way that I write it as a matrix product of 3 matrices. One I call U, the other one I call V, and one I call the matrix of the singular values, which is S. And then I can decompose this matrix as U times S times V. And S is a real and diagonal matrix, while U and V dagger are unitary matrices. This is something one can always do. In Julia, you type SVD matrix, and then you get these. Okay, good. And this SVD will help you to compute the eigenvalues of reduced density matrices. This is something for the interested of time. I kind of skip here. It's really just a few lines, but I really want to move on. But fundamentally, what happens if you take this matrix, you do a singularity decomposition, then what you have to do is you write the total matrix of the system again in this ket bra form. This is a pure state. And then you build the trace over the other subsystem N. And then fundamentally here, one has to compute this. And here one inserts the singular value decomposition there. And then one just uses the fact that U and V are unitary, meaning that the columns and the rows are orthogonal with each other. And then you will find that if you do that, you can write your reduced density matrix of the system as a sum over the singular value squared times some new basis state. Right? So what this is doing, you can think about this as a kind of general diagonalization of the matrix, of the reduced density matrix. These two unitary matrices, U and V, they define a new basis for the problem, for the reduced density matrix, such that the reduced density matrix is actually a diagonal matrix. And now you can easily compute the entanglement entropy from this just using the square of the singular values, which will give you these lambda values that I talked about before. Okay, very good. So this is what I said here. So now with the singular values here, you can compute just the von Neumann entropy. Okay, a few comments here, and this is one very important point I now want to really highlight. So if you were sleeping, wake up. Thank you. Okay, so with the singular values, I can can compute this entanglement entropy. But also what's really nice is, and an important point I will just I highlight it here. So the idea is now I can kind of compress the information of my big state. Right? Because these singular values squared, I know that they are a probability distribution. So just imagine that if I order them in terms of the magnitude, so I get some distribution of the singular values here, and fundamentally I have as many singular values as the Hilbert space size of my subsystem. But just imagine situations where many of those singular values are very, very small. So let's say I define just a number which I call chi. I call this the cutoff. Later in MPS one calls this the bond dimension. And then I just throw away this information of these small singular values. Right? So what this does is I just cut away pieces of my state representation, but I keep some essential information. Then if I do this, what it fundamentally means is I said before that the maximum entanglement entropy I get is the logarithm of this reduced Hilbert space size. But now the maximum entanglement entropy I get is the logarithm of this artificial cutoff that I introduce. Right? So that by doing this, what I do is I limit the amount of entanglement that I can get between my two parts of the system. In the most extreme case, if I only keep one singular value, I can only represent product states, and then I reproduce mean field. But the idea that I want to introduce with this matrix product state is that I just keep a bit more than this, and therefore construct a class of states which I can then use to do my simulations. All right. Good. So there's a very fun way to introduce this concept in action. So here I just show how this is done. But imagine that now instead of the quantum state here, I mean, the way I wrote it here is I wrote it as one big Hilbert space on one side and one big Hilbert space on the other side of the system. And let's just say, okay, this is just a matrix of dimension D. So a matrix is also just an image. Right? So let's say instead of a quantum state, I put here a matrix which are just some grayscale values. So imagine you have a number between 0 and 255. And this is for each of the pixels of this picture, you get one of these numbers. Then this picture of this cat is really just, it's a matrix. Right? And you can do this in Julia. You can read in a picture. If you have actually a PNG file, it just works really with this load command. Then it's just convenient to actually write these elements as floating point numbers. So if I do this thing here, I get something like that. right? So if for this picture here, I had a dimension of 1,536. So this would be my reduced Hilbert space dimension size, if you like. And now I get this big matrix with all of these numbers here, and each of these numbers tells you how dark or how bright this point is. Okay, and then what I do is I take now the singular value decomposition of this matrix. In Julia, as I said, it's just SVD of this matrix. It's going to give a U, S, and this matrix V. And now I can just plot the distribution of the singular values and make this plot here. And then what I get is I typically get something like this. So note here, of course, because I didn't normalize this picture, so it's not a proper quantum state in a way, because these are just, the norm is great. So that's usually singular values. They are all, if I sum up the singular values squared, they have to give me 1, because they are a probability distribution. But of course, here I get much larger numbers than this. But the typical thing is, you see that this picture has some structure in it, right? It's not just a random white noise picture. It has some structure, and therefore you see that you have very few large singular values, and then there's an exponential drop of the other ones. Okay, so it should mean that here, if I cut away a lot of these values, I can still keep a lot of information of this picture. And the same is true for quantum states, right? So generally, when you simulate some dynamics, you don't want to do just random stuff, unless you are Google. They want to do random stuff because it's the most difficult to simulate. But if you want to do something structures like Hamiltonians, which have some interactions, you're going to create states that's going to have some internal structure. It's very complex. You may not be able to identify it. But something is in there, and here you can use the singular value decomposition to tell you sort of which singular, which reduced density matrix eigenvectors are more important. Okay, so now one can do the following thing. I can now say, okay, let's just see what happens if I cut away singular values. So I introduce this cut of chi, and then I just only rebuild my matrix C, just from only the first chi columns of U, the first chi rows of V, and only the first chi singular values. Okay, and the first thing I can do is I set chi to 1, right? So I make the product state mean field assumption. And then what I see is I get something like this back, right? So you really lose almost all of the information of the picture, right? So here you couldn't even say if this is a cat or not. And then the idea is you can now repeat this and make this dimension a little bit larger, and then you start to see some features. I still say it's not enough to see a cat. This was chi equals 2, this is chi equals 16. So now you start to see, okay, this is start to looking like a cat. So if you're interested in the question, is it a cat or something else, then you can identify it. And then if you use something like 128, I choose here, it's really almost exactly the same picture, right? So here, if I take 128 of the singular values, which is a number still an order of magnitude smaller than my size of the Hilbert space, I get really all of the details, even the fine details, right? So singular value decomposition is also just an image compression technique. But the nice thing is now here we can apply this to quantum states if we do this bipartition. And it gives us a physical meaning, because the singular values tell us how much the entanglement entropy there's going to be between two blocks for my bipartition. And this whole business of MPS is essentially finding a state representation where I do this to compress a system of a many-body state. Yes? Well, you do, I will show an example, but you do exactly that. You run your simulation with chi1, with chi2, you make your chi bigger, and then you look for convergence. I will show an example later. Okay, but it brings me to the last part before showing some nice figures. So now we have understood this concept of this bipartite entanglement entropies. And now I want to show, or I want to at least just sketch the way of how this is used to write down algorithms for simulating dynamics in a many-body system. So the question now is, and this is where our diagrammatic notation again comes in pretty handy. So fundamentally, what I want to convince you is that a matrix product state is something if I take my coefficient tensor, which I defined before, right? So I have now an arbitrary many-body system. Before I said it was just a qubit system, but it can also be local bosons or anything, any composite system really. And I write it just as this object with all of these indices coming out here. And the matrix product state is if I take this object here and I write it into something like this. So I write it really as this tensor network. which is a network of smaller tensors which are all contract together to get the big tensor. And how do I do this? Well, I can do it with singular value decomposition. So singular value decomposition is also something I can write down in this diagrammatic framework. I kind of did it here. Right, I said before, if I have this coefficient matrix C, then this is a 2-index object, so this is a matrix. If I do this SVD on this matrix, it means I split up this matrix into 2 parts. And then I get the matrix U, which is this matrix here with 2 indices. I get the matrix V here. And I get this diagonal matrix, which I here indicate by this little circle, which I call the S matrix. Right? You can draw any shape that you want. There's no clear convention. Here, I did this little circular thing just to say that this is a real matrix, which is diagonal. Okay, now you see that I can actually transfer this high-dimensional tensor form into this matrix product tensor network form just by starting on the first index, for example. So I take this tensor, I can reinterpret my matrix by splitting up the first index, the small index here, and then I combine all of the other indices into one other index. So now this is a matrix. This is actually 2 times 2 to the n-1 matrix. And now I do a singular value decomposition of this matrix. And then I go to the next point, and I do it again, and I iterate through my big state. So I want to make 2 comments here. So first of all, of course, in practice, you never do this, because in practice, that would mean that you already have a very complicated state here, and then doing this would be actually quite expensive. But all of the problems that we looked at before, like for the ion trap problem, for example, we start with a product state in the beginning. For example, the nail state, which was spin up, spin down, spin up, spin down. And then it's actually easy to write down just this product state form immediately in the beginning, because the dimension of this connection here is then just 1. There is no tensor. There's just a bunch of vectors. The second comment I want to do is that if you do a singular value decomposition, right, so this C, especially if I do it in the beginning, it's definitely a non-square matrix, but it is a 2 times 2 to the power n matrix. Still, if you do singular value decompositions, then the dimension that comes out for this index here is always the minimum of these 2 dimensions there. Right, so that if I start on the edge here, what this means is that here, this new index that I introduce with this SVD, it can at most have the dimension d. For qubits, just 2. Right, and this makes kind of sense, because intuitively, this means that the entanglement for the splitting of having only 1 qubit on the side can only be maximally 2. Right, so only can be 1, the entanglement entropy. So I need maximally an index of 2 to capture possibly all of entanglement. But now if I keep doing that, then this dimension can get bigger and bigger and bigger, which means in the center of the system, I have potentially more entanglement between the different blocks. All right, good. A few other comments I wanted to do. So if you look at the literature, there's many other different ways of writing MPS defined. So here, the way that I did it there, I kept these singular values explicitly in my MPS. This is something which is also called the gamma lambda form, because these tensors here are usually called capital gamma, and then these ones here are called lambda. But of course, one can also just say, okay, after that, I multiply these singular values either to that tensor, or I can multiply it into that tensor to write it in this kind of cleaner form. Then the algorithms conceptually change a little bit, because if you have one nice thing aspect about this form here is that you can always think about these lambdas here. They're kind of the singular values for the reduced density matrix if you make the splitting at this point, right? And they are defined with these orthogonal matrices, right? So then you always know that if you keep this lambda explicit, you know what are the expansion coefficients in the spaces to the left and the right. So you always have a good basis for your reduced density matrix. If one starts multiplying these lambdas into these tensors, then this orthogonality goes away sometimes, and one has to be a bit careful. Okay, that's just one comment. The second comment is also the reason why it's called matrix product state. Now, all of these objects in here, they are 3-dimensional objects. They have 3 indices coming out. So another way to think about them is sort of as a matrix of vectors. Right? So imagine that you have these matrices here. They have some dimension, some row dimension, and some column dimension. And one is sort of this left index of the thing, and the other one is the right index of that thing. And then each element of this matrix is itself by a vector because there's another index coming out. And then if I again contract this thing all together to the state tensor, it just means that I multiply all these matrices back together. Right? So and now this is kind of a state which you write a matrix product state because it's decomposed as the matrix multiplication of these matrices. Some other nice things that one sees immediately is, again, this is what I actually mentioned before. Now imagine that you set all of these new virtual dimensions that are introduced. If I set all of them just to the dimension 1, right, then again I get a product state. Right, and you see it immediately, and this is how you typically start on with this nail state. You start with an MPS, which has bond dimension 1, which means it's just really a product of local states, and this obviously has no entanglement. Right, so the dimension that you use here, also called the Schmidt rank, is telling you really how much entanglement there is in between. So finally, one last analogy I want to do, and then I will go on to the algorithm and then show some results. Here's maybe one last final, very intuitive way to see, maybe to understand what we are doing here. Again, if I take like 2 spins only, right? If I take a product state, right, I can write really the state of the product state in a very silly way. I write it as a 1 times 1 matrix multiplied with a 1 times 1 matrix, and the element is the state. If I take the Bell state here, right, this one I cannot write just with 1 by 1 matrices. I need 1 times 2 matrices. But I can write it like this. I put my spin up on this element of the matrix, the spin down here, spin up here, spin down here, and now I do a matrix multiplication, which is here just, for this trivial example, just an inner product between 2 vectors. And then that means I multiplied this state with this, so I get up, up, the first term, plus down, down. Right, so but this is entangled. So this here you see entangled states, you need these matrices to be large. No entanglement, they can be 1 by 1 matrices. Right, that's another very intuitive just picture that can help to understand what's going on. All right, nice. So here comes now the conceptually, I think, very easiest algorithm, because of course I just introduced this concept, and there's a big amount of literature out there on doing now algorithms of how to update your state. For example, going back to the time evolution that I had done in the previous lectures, right there you have to just update the state by doing a unitary evolution with your big many-body Hamiltonian. So how can one do this? One very easy thing is the so-called TEPD algorithm, which was introduced here in 2004. And it's conceptually actually just only an algorithm that tells you what if you just apply sort of a 2-side unitary to your MPS. Just like in a quantum circuit, you have a 2-qubit gate, and you apply this gate to your state. And the algorithm to update the state is only telling you how to update these 2-side unitaries. But it turns out this is actually enough if you want to do time evolution of a many-body state. And the reason why this is enough is known because there are these so-called Trotter decompositions. So this is something, this is very, very old actually. It has come up, I think, the first time again in this quantum context when there was this first paper on how to do like a simulation of a system on a digital quantum computer. Because also on a quantum computer you only have usually 2-side gates. So the question is just how to decompose a big unitary into 2-side gates. And this is what this Trotter decomposition does. An excellent paper is this one that I reference here. Because the trick is really just that you say, okay, you have some Hamiltonian, which typically has just some 2-body interactions. One can also do it for larger terms. But imagine you have a Hamiltonian which just has this pairwise interaction between some of your composite parts of the system, so qubits, for example. And of course, in general, these terms, they don't commute with each other. Right? So in general, if I want to build the matrix exponential of the full big Hamiltonian, I cannot just do this. I cannot just say this is a product of exponentials of the small parts of the Hamiltonian because they don't commute with each other, right? If they would commute, then I can do that, but they don't in general. So the whole business of this Trotter decomposition is just to find the corresponding order of applying this little two-side gauge such that one minimizes the error that one makes from the fact that these things don't commute with each other. Right, and there are some very elaborate, I mean, this is what this paper tells. It gives you a prescription, for example, fourth order decomposition. You apply your gates in certain orders, and then you magically get errors that are very small. Of course, if you would do that, this would be like the first order decomposition, just writing as product of just tiny gates. This is always going to be exact if you make this time step extremely small, right? But then again, here you would have a first order method if you just do this, and this is usually not a good idea, as we have seen the last time. All right, so if I have analyzed or understood that it's enough to just apply two-side unitaries, I can use this TBD description, which really just tells you contract this two-side gate into your MPS. What then happens is you end up with a term like this, and then you have a problem because this is not a proper MPS anymore. So then what I do afterwards, I do a singular value decomposition of this matrix here, split it up, and bring it back into MPS form. And that's it. Now, this is also very nice because here, what you see is here, if you apply this two-side gate, then you see that for this part of the splitting, I have the left block and the right block. Now I see that here, actually, if I do the SVD, then the new dimension that I introduce here, right? Let's say I have a dimension chi and a dimension chi here and a dimension d here. Then the dimension that comes out now new in between here is actually d times chi, right? So if I have qubits, then the singular value decomposition is going to give me a new index which has twice the chi that I had before. Right now, this tells you that two-side gates lead to entanglement because they grow this dimension. They grow the potential entanglement between these blocks of the system. So at that point here, of course, I cannot do this forever because at one point these bond dimensions, they also grow exponentially. So I need to do a truncation. So what one can do is one can define this truncation error just summing up all of the singular values squared up to this new dimension. And since my singular values give me a probability distribution, so this gives me really a probability weight that I cut away from my distributions. And this is the error that I make in the approximation. But it's very controlled because I can keep track of this error after each gate application that I do. Okay, and that's the TBD algorithm. And really, I mean, I really didn't have time to do a tutorial of this, but it's conceptually really not difficult. All what one needs is one has to write this Trotter decomposition. This is something independent of MPS. And then here, one only needs to do this contraction operation. The bottleneck is going to cost you chi cubed operations. Right here, one shouldn't just blindly contract everything. There's an optimal way of contracting this. Maybe something to think about. But it's going to cost you chi cubed operations. And then one does an SVD. And then one brings it back into normal shape. And then if one implements this, it's quite easy to do these large-scale dynamic simulations. All right, I have 15 minutes left, so just enough. So just I want to do a quick overview about what's out there. So there's a lot of stuff since 2000s or so. A lot of different algorithms out there. A funny one is actually, as you may have heard about this in the literature, it's the so-called DMRG. It's called Density Matrix Renormalization Group algorithm. This was already invented by Stephen White in '92. And at that time, there was no idea of matrix progress state around in this community. Actually, in some other communities, in the math community, they already knew about MPS. They called it tensor trains in this community. It's the same thing. But this algorithm was a way of finding the ground state of a many-body system, but it wasn't using MPS to formulate it. It was just formulated in a more abstract way. But then with MPS, one can actually understand this algorithm much better. By the way, it's called density matrix renormalization group because you think about the reduced density matrix and you renormalize it by throwing away these eigenvalues. That's the approximation. That's why it's called that way. And what it really is in the MPS language is sort of, one starts with one picks out one of these MPS tensors in the system, and one just locally just minimizes the energy. So one finds locally the tensor that gives locally now the minimal energy of the total state. Then one updates this tensor and one moves on to the next one. Right? So DMRG is a variational technique to update these tensors in this MPS, doing sweeps through the system and lowering the energy finding eventually the ground state of the system. Also, what's very important is now I introduced this concept of MPS for the state, but one can also do this for Hamiltonians. Right? One can also do like matrix product operators. So I can write a Hamiltonian like this. It has two indices coming out on two sides because it's a Hamiltonian. And then with these Hamiltonians, if one writes it in this form, one can write very elaborate algorithms of update MPOs, also variational algorithms to update MPOs, and so on. There also is a lot of literature out there to generalizing this idea to two-dimensional systems, right? Because fundamentally the way that I decompose my state is 1D, which does not mean that I cannot treat higher dimensional systems with MPS, but I just have to kind of order my system in some way. So naturally, if I have one-dimensional systems, it's most efficient to write it that way because I have a natural one-dimensional geometry in my system. For 2D, if I write an MPS, I have to think about making a snake kind of through my system in some optimal way. So it is also a generalization of this MPS to two-dimensional, which is called projected entangled pair states, yet another acronym. And they are very nice, actually, conceptually. In practice, they are actually not very, very useful, unfortunately. Also, people have been writing down sort of this kind of trees with these tensor networks. This is called, for example, the multi-scale entanglement renormalization ansatz, or MERA. This is sort of an idea of kind of coarse-graining this entanglement in some other virtual dimension. Again, very interesting conceptually, not so useful actually in practice. So for practical simulations, MPS are just actually the state of the art nowadays still, I would say. Okay, one can do a lot with matrix product operators also for a density matrix. That's a topic I have personally also worked in a lot. And then there are things like so-called ITBD algorithm. Think about you want to simulate an infinite system, but you have a Hamiltonian which has only nearest neighbor term. Then you have a symmetry, which is translational invariance, so you can always shift your system by two sides. And then one can, for example, write MPS, which is just AB, 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 but then these tensors, they are all the same. So you just keep track of two of them. And then instead of just a finite, you actually can simulate an infinite system. And if you're interested in this, I cite here a review article, which is actually quite old by now, but I still think it's the best, which kind of summarizes a lot of these ideas with MPS and gives you a guideline for all of these algorithms. Okay, so this is the summary of what's out there. Good, so, but finally, let me spend the last 10 minutes or so just to show you now how this works in action, really just this TBD algorithm. And now that's why I showed you this bosonic part in the beginning, because now I want to show again an example of really this Bose-Hubbard model physics. So this is something what typically happens in the Bose-Hubbard model. A while ago, it was quite popular to do the following experiments, and people really did this. So the Bose-Hubbard model, I have introduced it a few times already. It's really this model where you have a boson sitting on one side, and then this boson can hop between a neighboring side with this term. So this is really, again, exactly the same as just a hopping term in an infinitesimal grid, but here just in a real lattice, in particular in an optical lattice. And then if two bosons are on the same time, you get an energy offset, which is U. Right? So, and then this term here, this is the same term as this term B dagger, B dagger, BB. Just using some commutations, one can write B dagger, BB also as n times n minus 1, where n is the bosonic occupation operator. And then you see here that if you have 2 on the side, you get here a term 2 times 1, so you get a shift U if you have 2. If you have 3 on the side, then you get sort of all the pairwise interactions. Right, so this is an on-site interactions between bosons. Okay, and then what people have done is they started with sort of making these experiments. So you load a BEC into a so-called optical lattice. You will learn how this works next week. Fundamentally, you just use the AC Stark shift of light to trap atoms, make them very cold. So one can really engineer this type of lattices. And then one starts in a situation where the lattice is very deep, and then one can suddenly make this lattice shallow. So what this means is that one can suddenly change the interaction strength from something which is very large, where you have one of these atoms sitting per side, to something which is very small. And then all of these atoms start to tunnel, and the whole thing evolves as a coherent evolution. So here in this plot, you see what happens then in terms of the entanglement entropy. So what I plot here is really for a chain of like 100 of these bosonic particles. And this is the entanglement entropy between two blocks of 50 sides on the left and 50 sides on the right. And here I come back to the question that I had earlier, how do you check if it works? Well, in practice, you just check by rerunning the simulations using a TBD algorithm, just always increasing the bond dimension. Right, so here I show an example where I take this bond dimension, I write it as 2 to the power of some number L. So if L is 4, I have a bond dimension of 16 only. Remember the cat, 16 was the one where you could not maybe say it's a cat or so. And then fundamentally, of course, my entropy is limited by the logarithm of 16, which is, of course, just 4. So I cannot access states which have more entanglement entropy than this horizontal line. And indeed, if I do the simulations, I start with a state with one boson per side, so it's almost a product state, almost no entanglement in the system. And then this entanglement starts to grow as a function of time, but then I cannot keep track of it, and then I level off here. Right? So at this point, if I'm interested in the evolution of entanglement entropies, at this point, I cannot follow the evolution any further because the Hilbert space I use is too small. But then I can make it larger. I make it 5 here, then it goes to 5. I make it 6, then it goes to 6, and so on. And the more entanglement I allow for, the more I can follow the simulation. And if I show plots in a paper, I have to make sure that everything I show is converged in this bond dimension so that the results converge to one particular value, together with keeping track of these truncation errors that they have to remain small all the time. Okay, so but of course, here in this case, I say just 4, 5, 9 as it would be easy, but it means an exponential increase of this bond dimension. Right, so here now you have a nice connection that you see that this phenomenon entropy grows linear as a function of time. But then this means that, I don't know why I do this, sorry, this is wrong. It grows linear as a function of time, but then it means that your bond dimension has to grow exponentially as a function of time. Right, so if you do these experiments, then you can actually say that this is sort of hard to simulate on a classical computer because the entanglement grows too fast. And then you can say, yay, quantum advantage. Unfortunately, of course, it's still also, again, kind of a boring evolution. This is very similar to what I showed last time, where you then, when we were driving this Ising model and we saw that everything just goes to 0 because subsystems effectively thermalize. Because that's always the thing. If you have a subsystem and if you have large entropies here, then if you pick out a small subsystem, it's going to be very entangled with the rest. So it's going to just have high entropy. So it's just going to start to look like a thermal state. So then there's actually nothing exciting to get out from your quantum simulator there. The message is if you want to get some information out, you have to also look at some very complicated high-order correlation functions to get some useful information. And then you actually need a lot of statistics to collect those. But okay, that's just as a warning. Okay, so this is, but still linear growth, you can say linear growth, and this is mathematically also really proven. If you have a linear growth, then this is going to be difficult to simulate classically. But then, of course, there's many other situations where you don't see this linear growth. Famous examples are if you add some disorder to your system, then this linear growth actually stops, and it just starts to become a constant sometimes even, or it just becomes a logarithmic growth. So that makes it easier. If you go to an open system, if you couple to some other path, this usually destroys entanglement, and then also entanglement growth slows down, and you can simulate it more efficiently. So fundamentally, anything that makes it more classical makes it more easy to simulate, obviously, because you have a classical computer. One other example here, this is just some self-promotion of work from actually a long time ago. Quite surprisingly also, if you introduce long-range interactions, they also lead to a slower increase of entanglement in the system. Right? So this is, again, our beloved transverse Ising model, where you start with a state where you rotate all the spins in one direction. And then if you start with this state, and if you have relatively short-range interactions, here this alpha is, again, this decay exponent that I used all the time in the lectures before. You see here that you get this linear growth. So here you get, again, this kind of buildup of entanglement. But if you make the system more and more long-range, actually this entanglement growth starts to slow down more and more, where at one point it actually becomes a logarithmic growth as a function of time, which is very interesting, something we pointed out in this paper back in the days there. And a way to understand this is going to an extreme limit. Going to an extreme limit, for example, where you put this alpha completely to 0 here, And when you have really all-to-all interactions, then all of the spins talk to each other in the same way, because then you introduce a permutation symmetry in the system, and then you can describe everything just as one collective spin evolving. And then everything becomes very easy in the sense that this entanglement just stops growing. It just goes to a value which is something proportional to the size of your system, and it keeps staying there. So just to show you an example here. Okay, and finally, I want to come back to the example of, to close the circle, to the Gross-Petersky equation example where we had this physics, where I had this dynamical instability. Now, there were very nice experiments. This was a long time ago in 2007 in the group of Wolfgang Ketterle, and they kind of tested this dynamical instability problem. So again, this is optical lattice physics. So they loaded a BEC in an optical lattice. And then they did exactly what I did with the Gross-Petersky equation. I just gave the system a kick. So this is not a very deep lattice. It's a very shallow lattice. So you have very effective tunneling. So it's really like a weakly interacting grid model of the Gross-Petersky equation. And then at time equals 0, you start to kick this BEC. Technically, actually, they didn't kick this BEC, but what they did is they made the lattice move. Right? You can detune this lattice, then the whole lattice was moving in one direction. And then depending on how strong they make the kick and how strong the interactions are, one finds regimes where this BEC or superfluid state just remains superfluid. But then if I go across this, at one point it becomes completely, it disperses. You destroy this BEC. So you can destroy this BEC by kicking this lattice, which is equivalent of just moving it very fast, or you can destroy it by making the interaction strong enough. And this was in 3D. And they did the mean field calculation, and the mean field calculation works perfectly. But then if you do the 1D calculation, what one could see is that actually there is no sharp crossover. There is no sudden kick where the BEC gets destroyed. But if I just kick it a bit more, it gets destroyed a bit more. So there is this kind of smooth crossover between the two behaviors. And if one does a mean field theory here, one just sees that things are completely wrong. And this is something that one can test now with this matrix product states. Proud that I did it. It was my very first paper that I published. So one can use these MPS algorithms now to redo this experiment really on a computer. It's really easy to do with all of the tools that I just explained to you. And then you see, for example, if you kick this superfluid state, here I plot the momentum distribution. So one starts with a sharp momentum distribution. So all of the particles being in momentum states, which are placed here. And then as a function of time, this just goes away. So your nice, sharp, macroscopic occupation of one state, you start to lose. So you can ask how many particles do you have in sort of one of these macroscopic states. It's called the condensate fraction. And then if you kick it very weakly, this condensate fraction remains stable. So here your superfluid remains a superfluid. But then you kick a bit further, and then this goes down as a function of time. You lose your condensate. And then one can really compute this kind of nice crossover between regions where you lose your condensate and others where your condensate remains stable. And the mean field results give something which is completely wrong. Right? So that's what I meant before, this kind of sharp thing that when I kick the BEC, like in this 1D situation, it would just stay together all the time, and then I kick it a little bit more, it would go away. This is something which is an artifact of mean field theory, which is just bad in 1D. And MPS allows you to redo the calculation and get the more correct modeling of this experiment. All right, this is it. Perfectly on time, I may say. So let me just finish by doing a whole summary of all of the four lectures that I did. So really what I was doing, I was kind of giving a broad tour about numerical methods for simulating large-scale quantum problems with a lot of hand-on examples. Just keep in mind a little bit how to store numbers in a computer memory. Just important to know the fundamental precision limits that one has, and just the linear algebra of quantum mechanics, so exact diagonalization. So the easiest way is always a full, complete diagonalization of the problem. We did this, and this solves really the Schrödinger equation. If you do this, you can do anything you want. Then you can use the fact that Hamiltonians are usually sparse matrices. So one can go to these Krylov space ideas just to double the system sizes that you can effectively deal with. Okay, but then in the first two lectures, we still were always keeping the quantum state exact, which fundamentally limits you to something like really 30 qubits max. Of course, if you go to a gigantic GPU cluster, you can do a bit more, but still you have this fundamental limit. And the way to go over this limit is just to find approximate representations of your quantum state. The most extreme approximation is this mean field approximation, which neglects all of entanglement in the system. Then you're really in a tiny corner of your Hilbert space. You get typically nonlinear equations. You can solve them with ODE solvers like these Runge-Kutta methods that I talked about, especially the fourth order method here. It's a pretty cool method to use. But then there's this nice thing what I talked about today is that there's a generalization of these product states, not only to the little point here, but also to states which occupy a bit bigger fraction in Hilbert space. And MPS, they have this nice cutoff in this bond dimension, which is a cutoff to the entanglement between splittings of your system. And you can use this as a knob to kind of control the amount of entanglement that you allow in your state. And then you can run simulations with the states, making this entanglement more and more until you get convergence. And then you actually reproduce the exact dynamics in the system. So a takeaway message is really very important. It's not really this number of systems that you have. So it's not the qubit number for a quantum computer that makes like the calculations of the thing hard. It's not the number of the particles you have. But the key quantity that really tells you how hard things are to compute on a classical computer, then it's really the entanglement entropy that matters. Because if this is low, then I can use this MPS states to simulate it also classically. So that's maybe one take-home message. If you take one, then take this one. Thank you. Any more questions? If not, dinner.